So now we have known how a dynamic model is constructed from scratch for the hard disk drive system. We have also seen how simulations can be done to analyze the properties of the system. Let's now go back one step and review this piece of mathematics that will help the analysis extremely simplified. This is Laplace transform for continuous time system. Let's start with the continuous time system model first. Let's think about when we have transformed the system from one domain to another, how simplicity can be introduced. To start with, I will give you this one little piece of calculus to motivate you. This is an infinite summation. Summation from n from 1 to infinity of this oscillating type of signal. So it's -1 to the power of n plus 1. So it oscillates between -1 and 1 in the numerator. And in the denominator, it keeps decreasing as n increases. How does this equal to? I will tell you this is a convergent series. It converges to something that's constant. If you review the calculus a little bit, you may find the procedure to solve this. But how does this relate to Laplace transform? If you go from the pure calculus way, you go back to read the calculus books, you may find procedures how to do this that will involve Riemann integral, Riemann series, etc. Okay? It's not as easy as something like this, right? Infinite summations or integral is always a little bit more trickier than something, for example, like this. If I have integration of, for example, 3x squared dx, this is very easy. This is, we know, it will be something that's finite. So it turns out if we view the problem from a different angle, it turns out if we introduce Laplace transform, actually, we can reduce the problem into something like this, something that's very easy. So to do that, I will need to introduce a little bit of the basic terms of Laplace transform. So Laplace transform was introduced by this French mathematician, Laplace. Laplace is actually very famous. He has done many other things besides Laplace transform. He is regarded as the French Newton or Newton of France. He's related to many other names. And two names that are interesting to observe is he is 17 years younger than Lagrange, who is a major person in many modeling process. And then he studied under this mathematician, D'Alembert, who actually is very famous, who is the co-discoverer of the fundamental theory of algebra with Gauss. So D'Alembert, the fundamental theory of algebra, as a side note, it tells you this very intuitive nowadays, but very difficult to prove concept at that time. It's basically about this. If you have a second order equation like this, x squared equals to 1, then we know that how many roots it has? 2. If it is 100 times x 100 plus, let's say, x 91 equals to 1, then how many roots the system has, the equation has? 100, right? So this is basically the fundamental theory of algebra. It gives you how many roots you have given the order of the equation. Anyhow, Laplace was in that period of time where a lot of interesting things were discovered. The Laplace approach to ordinary differential equations is as follows, illustrated in this picture. We know ordinary differential equations such as this one, it relates to differentiation and hence integration, right? And integration, sometimes it's easy to see, it's very trivial, but sometimes it's not. So solving an ordinary differential equation directly from the top line to the bottom left corner is sometimes not as trivial. It may be doable, but it's not as trivial. It's at least not as trivial as simple add, subtract, multiply, and division. Arithmetic, in other words, that's simple. That's extremely easy. That's what you learn in elementary school, right? So at least we know integration is not as easy as this, arithmetic. The Laplace approach to ordinary differential equations gives you this path on the right-hand side. By applying the Laplace and the inverse Laplace transforms, we can transform the ordinary differential equation to algebraic equation and use simple add, subtract, multiply, or division to solve the problem. So that is really powerful. And once we have the algebraic solution, then we can go to the time domain ordinary differential equation solution using inverse Laplace transform. So that is the essence why this is such a powerful tool. To look at this picture in more details, let's go to a few places. Let's start from here, from the definition of Laplace transform. The definition is transforming a signal to a property in another domain. So in other words, it relates to functional analysis. To do functional analysis, there are a few fundamental domain fundamental definitions we need to be equipped with. So let's review them over here. We say a set is a well-defined collection of distinct objects. So a set of integers, positive integers, can be 1, 2, 3, 4, 5, 6, etc. A set can be finite or infinite. So this is a finite set, and the set of positive integers is an infinite set. We say R is the set of real numbers. So it's both integers as well as non-integers. It can be 1.3, 1.5, etc., in addition to the integers. If we add a little bit more to the set of real numbers, we can have capital C. We use this to denote the set of complex numbers. So square root of -1 now is included in the set of C. We say 1 belongs to R to show that this element is a member of the set. So we use this notation, reads as belongs to indicate this relationship. 1 is an element of R. 1 is also an element of C, for example. And we say R plus is the set of positive real numbers. We add a plus to indicate it's a positive real number. And finally, when we use equal and then put a triangle on the top, we say defined as. So if we say y equals to 3x plus 1 with a triangle above the equal sign, then we're saying y is defined this way. So these are the basic sets that we work with in this class. The Laplace transform is defined over this continuous time function. So it is important to recognize the continuous time function is a mapping, in this course, is a mapping from R plus the set of positive real numbers. So it can be infinite time. It's a time domain. Time can only be positive for dynamic system to analyze. So it's a mapping from R plus to R to a single number in R. And then we use frequently f to indicate f is a function in time domain. So ft is a continuous time function, for example. And then we assume that all the dynamic system that we work with, we start looking at it from time t0, t equals to 0. So we assume that the function ft is 0 for all the negative times. The Laplace transform, now the single most important definition is here. The Laplace transform is defined as integration of this function f, continuous time function f, over the entire time domain t from 0 to infinity. And then this f is multiplied with this exponential function e negative st. That's the definition of Laplace transform. Then we can, after this definition is set, we can start analyzing a dynamic system. Now, anytime that we see an infinite integral, it is important to ask the question whether this integral actually converges or not. So for Laplace transform, it turns out this integral is actually very easy to have a finite convergent value. There are just two sufficient conditions that we see very commonly for realistic, real-time, real-world signals. The two sufficient conditions are if the signal we require it to be piecewise continuous. It can have jumps, but it will have to be piecewise continuous in each interval that we can break it down into. So this example on the screen is a piecewise continuous function. It cannot be some function that just have random jumps, right? So an extreme example is discrete time signal. Discrete time signal, it jumps, it doesn't have values between these k equal to 1 and 2 finite discrete time indices. So that's the first condition. It's piecewise continuous. And the second condition is this. The Laplace transform definition, you can see it has this exponential function inside. Exponential function is actually very advantageous. It has many nice properties. So looking at this one is not actually difficult to understand that a Laplace transform, for it to converge, we will require that this function, f, it cannot increase crazily fast. It cannot increase faster than any exponential function in the end. If this keeps increasing really, really fast as time goes to infinity, then this exponential function, it turns out we can no longer control what happens at infinity, right? Exponential function, many of them will die out eventually, will converge to 0. But if this is too big, if this one is too big, then we cannot control what happens at infinity. So intuitively, the second sufficient condition is that this signal f, it cannot increase faster than the exponential when time happening at infinity. For the example on the screen, it is piecewise continuous, and it's actually larger than exponential function at the beginning. However, it is okay to have this property over here, as long as what happens at infinity when time is really, really far away, we can still bound the signal exponentially somehow. So that is the second sufficient condition for Laplace transforms. These two properties are usually satisfied in practice for us, fortunately. Now let us do some simple exercises and take a look at some typical signals in practice. The first is an exponential function. This is a most basic signal that if you understand this one, you can relate to many other Laplace transforms. So let us do this a little bit. Exponential function, it can happen this way, or it can also happen this way. And then this is 1. So it can be exponentially increasing, it can also be exponentially decreasing. The Laplace transform of this signal is infinite integration of e, now substituting e negative at inside, then we will have e negative a plus s t dt. The benefit of exponential function is that dE negative bt, this equals to negative b e negative bt. So the derivative of exponential function is also an exponential function. So therefore, this one is nothing but dE negative a plus s t and then negative s plus a from calculus. So therefore, the final result is simply evaluation of, there is a gain, 1 over negative s plus a, and then e negative a plus s t evaluated the difference between its value at infinity and its value at 0. So it is very easy to see that this, when t equals to infinity, we have e negative a plus s infinity, which is 0, minus when t is 0 is e negative 0, so the entire thing is negative 1. And therefore, the Laplace transform of exponential function e to the power of negative at is 1 over s plus a. So that is the detailed calculation of the Laplace transform. We have this very important Laplace transform pair. Exponential function, first order the exponential function equals relates to 1 over s plus a in the Laplace domain. With this, we are just one step to the infinite sum example at the beginning of this section. Using the exponential function Laplace transform pair, we can very easily see that if it's a step function like this is 1 over here, then the Laplace transform is very easy, because a step function is nothing but an exponential function with a equal to 0. So a step function is a special case of the Laplace transform calculation we did in the previous slide. So we know e negative at corresponds to 1 over s plus a. Therefore, when a equals to 0, the Laplace transform of the step function is 1 over s. So this actually will immediately help us with the infinite summation calculation. Any questions so far? So let's now look at this one. How can Laplace transform help with this infinite series over here? The way to look at it is actually as follows. We know that 1, the step function, relates to 1 over s. In other words, 1 over s is, by definition, is a Laplace transform of this signal. 1 of t times e negative st dt. This is just a by definition 1 over s. Because it's a Laplace transform of a step signal, it has to satisfy this. Now, we can change notations. You can see if you replace s with another notation, let's say n, this equality should still hold. We're not changing anything. And then, if you recognize that fact, then you can have the summation from n equal to 1, from n equal to 1 to infinity. This one is actually nothing but I replace 1 over n with this Laplace transform integral. Without breaking the equality. This seemingly more complicated step actually will immediately turn out to be actually helping. So we can see my integration is over t. So it's not over n. Therefore, I can bring the integration to the front before the summation. And then inside is this oscillating minus 1 and plus 1 multiplied with this exponential of negative nt. This one, we can see it actually is very easy. It's negative 1 times negative 1 n e negative t to the power of n. In other words, this term is negative e negative t n So this integration and summation is therefore negative. I can put a negative and then negative e negative t n dt. So now we're just going to use something very fundamental to solve this step. I noticed that here, inside, this infinite summation is about n. It's not about t. So I can do this infinite summation inside first, and then care about t afterwards. For this infinite summation, is nothing but a special form of this. If I treat negative e to the power of negative t as x, I introduce this notation x, then this is nothing but calculating a simple power series, which we know. What does this equal to? This is x plus x squared plus etc. We know that if you do 1 plus x squared, etc., this equals to 1 over 1 minus x.
You may not be on the screen. It might not be ready.
Which one?
Oh, never mind.
Let me use a different color then as a side. Okay, so as a side note, we know that if you do 1 plus x squared, etc., it equals to 1 over 1 minus x. So therefore, this infinite summation, it equals to 1 over 1 minus x minus 1, or in other words, is 1 minus x x. So we know how to calculate this infinite summation. So using this fact, we know that this inside, it equals to negative e negative t over 1 minus negative e negative t. So in other words, it's 1 plus e negative t at the denominator. So therefore, this infinite summation now becomes an integral that looks like this. And this integral is actually much more simplified to calculate compared to the original one. Because we can see that this equals to, if we denote u to be 1 plus e negative t, then we can see that this is negative u, and then in the numerator is going to be 1 minus u, and then dt. And we know dt, so if I see u is 1 plus e negative t, we know that du dt equals to e negative t negative. Just from chain rule differentiation. So this equals to e negative negative of u minus 1. Or in other words, 1 minus u. Use a little bit more space. So from here, by definition, we know that e negative t equals to u minus 1. So the whole thing is 1 minus u. So now we can see from this property, we can see that from basic calculus is du is 1 minus u dt equals du. So in here, therefore, this one is integration 0 infinity 1 minus u times dt. You can see we have already seen that this is du, and then in the denominator is u. This is easy integration, therefore. So we didn't use any complex calculus tricks over here. Then we know that this is log negative log of u from t equal to 0 and to infinity, actually. So I would do t equal to 0 to infinity. Let's add one more slide. So we have now, let's copy what we have. We have now this infinite summation it equals now this simple integration with the relationship that u equal to 1 plus e negative t. So this is a new dummy variable. We introduced this u over here. And then this integration is from 0 to infinity. So we only need to find out when t is 0, what is u integrating starting from, right? So when t is 0, u equal to 1 plus e negative 0. So u equals to 2 when t is 0. And then when t is infinity, this u equals to very simply just 1. So this integration is from 2 to 1 for u. And then therefore is from 1 to 2 with the negative sign in the front. And then du over u is log of u. So the whole thing is log of u from 1 to 2. And then which equals to log of 2 minus 0. That is the final value for this convergent infinite series.